Hello everyone, my name is Tian. I come from Beijing Institute of Spacecraft System Engineering. My paper is about the design of universal software architecture for spacecraft autonomous thermal control. Introduction. As a basic function of the spacecraft, effective thermal control is essential to ensure proper functioning of the devices in spacecraft. Thermal control can be divided into two categories, the passive thermal control and the active thermal control. The research object of this paper is the active thermal control with the electric heater as the control means. With the evolution of intelligent spacecraft, it's not necessary to set a specific device for the thermal control. The common choice of current spacecraft is to integrate the thermal control function into the onboard data handling system, which is OBDH system. With the construction of a space-based information network, the performance improvement of spacecraft has generated an urgent need for precise thermal control. Traditional OBDH system is insufficient to accomplish more and more heavy workload. To satisfy the urgent need of intelligent and networked spacecraft, the avionics system is rapidly evolved. Based on avionics system, the development of avionics software based on software components is promoted. Electric heater is widely used in auto-active thermal control. Based on avionics system, thermal control of spacecraft is evolved towards the direction of precision, intelligence, and joint optimization design with other fields. The joint optimization design can be further divided into two directions. The first is to ensure the energy balance of spacecraft, and the second is to optimize the impact of thermal control on energy. Those two design directions are not in conflict with each other, and they can be used in thermal control simultaneously. The questions and solutions. Though there are various joint optimization designs, the thermal control software architecture of current spacecraft has not been unified yet. The amount of Chinese spacecraft in orbit will grow significantly in the foreseeable future. Generally, the design of thermal control can effectively help the design and implement of onboard software, promote flight support effect, and increase the onboard maintenance capability of avionics system. So, to improve the scalability and the portability of thermal control software, a universal architecture is proposed in this paper. First, we must do the analysis of control elements of active thermal control. To accomplish precision thermal control, it's necessary to analyze and optimize the performance of control elements, such as temperature accuracy, the thermal control circle, the thermal control time slot, the heater switching model, and the energy constraints. Based on these control elements, we can finally decide how to design the software control process. First, the temperature accuracy. Temperature accuracy depends on both the accuracy and the processing of raw data. To improve accuracy, AD converter with better accuracy and stability should be selected. And as an effective way to solve the problem, the raw data can be converted into temperature according to the harmless calibration voltage of the accuracy circle. Second, the control period and the time slot of thermal control. The control period influences the responding speed of temperature change. The amount of time slot determines the granularity of the duty cycle. The foundation to realize shorter control period is higher computing power, and the foundation to realize more time slots is the heater bench switching capability. The third is the switch model of heater. When the heater needs precision control in a control period, the duty cycle control should be applied, and to reduce the temperature fluctuation of the controlled object, the bench switching of heater on-off state is a good choice. In correct avionics system, the phase command is replaced by the electronic switch, which has the ability to bench switch the heater on-off state rapidly and effectively. And finally, is the energy constraints. When the spacecraft energy imbalance is predicted, what shall we do? We can do two things. The first is the thermal control should be transferred to the minimal working model to decrease the number of active heaters and reduce the power consumption of spacecraft. And the second thing, we can adopt it to a time-sharing switch model to reduce the peak power consumption of spacecraft. Based on the analysis of the control elements, we designed a universal software architecture. Based on the commonness and the characteristics of existing solutions, thermal control is divided into 5 key steps in our proposed architecture. They are the temperature raw data acquisition, the temperature raw data preprocessing, the thermal control logic, the energy optimization constraints, and the heater switching control. Configurable software components are introduced in 3 elements. They are the temperature raw data preprocessing, the thermal control logic, and the energy optimization constraints. Different spacecraft can insert, modify, or expand the software components to achieve specific intention. And as the basis of proposed software architecture, the avionics system consists of system management unit and data interface unit, as shown in Figure 1. The devices adopt universal module designs, and so the DIU has the same computing power as the SMU, and the data exchange among modules is realized through the internal bus inside the device. The communication between the device is implemented by intra-satellite data bus. This is the organization of our system. As we can see, in the system, the SMU is in charge of the uplink of downlink of the spacecraft, and the SMU and the 2 DIUs exchange data by the intra-satellite data bus. The 3 devices share the same kind of modules, such as the general purpose computer. We can see the SMU has 3 GPC module, and the DIU1 have 2 GPC module, and both 3 devices have bus communication interface. The DIUs also have the same kind of data acquisition module and the same kind of power drive module. The heater switch is controlled by the power drive module, and the safety switch is controlled by the command module, and the thermal control is in DIU. And the independent power drive module ensures that DIO can bench switch heaters on-off state in a short time slice. So the action of heaters can be described as a matrix indexed by the heater and time slot, such as shown in this picture. This is the heaters. This is the time slots in a control period. We can see there are 10 time slots in a control period. So each element in the matrix represents the on-off state of a heater in a certain thermal control time slot. Thermal control can be abstracted as updating the matrix according to the temperature particularly. And this is the control process. We can see the control of a thermometer is divided into two modules, the temperature raw date acquisition module and the temperature raw date pre-processing module. The control of heater is divided into three modules, the heater control logic module, the energy optimization constraint module, and the heater switch control module. Every time the autonomous thermal control process is called, the TRDM is first executed and the raw date is collected. And when the thermal control process runs, it directly obtains the latest raw date from the global data pool and refresh it into the semester data structure. After the TRDM, the TRDPM is executed. In the TRDPM, configurable software components are provided. Users can use different plugins to achieve the raw data format conversion, the data statics, the thermal semester health monitoring, and other functions according to personal needs. Through those two modules, the processing requirements of semester in existing spacecraft autonomous thermal control can be met, and the input data needed for heater control can be obtained. The input of HCLM is the control state of the heater and the output temperature of the semester. And the output of HCLM is the switching matrix of the heater in the new control circle. The matrix illustrates the distribution of the switching state of heater. And the EOCM takes the total power consumption of each time slot and the energy constraint as input, judge whether the power consumption can meet energy consumption constraints or not, and outputs the switching choice. Output the switching choice of the heaters when current power consumption couldn't meet the energy constraint. When the power consumption is at risk of exceeding the energy constraints, the control state of the heater is switched according to the corresponding storage, and the HCLM need to execute again. If the power consumption of the switching matrix output by the HCLM can meet the energy constraint, the new on-off matrix is published, and then the HSCM is executed, and the heaters are benched switched according to the on-off matrix in each control slot. The development of thermal control software in 4 satellites is analyzed and evaluated, and compared with the traditional architecture of spacecraft thermal control software. Proposed software architecture has achieved significant improvement in the development efficiency and the software complex. And the software complex is effectively controlled. And as we can see in this figure, the development cost is reduced by 66.5%, and the efficiency is increased about 3 times. And as we can see in this figure, after the adoption of proposed universal thermal control software architecture, the development efficiency of satellite 3 and 4 greatly improved, and at the same time, the robustness of thermal control is also improved. The conclusion: based on the development analysis of existing spacecraft thermal control requirements, universal autonomous thermal control software architecture is proposed. The configurable software components can realize common control logic of thermal control and can effectively support the personalized control needs, energy constraints, and of different spacecraft. And the application of proposed software architecture doesn't increase the occupation rate of system resource, and it can significantly improve the efficiency of software development, reduce the complexity of code design, and improve the robustness of code. It has been applied to several remote sensing satellites and deep space probes, and have obtained positive effect. Thank you. That's my presentation.